Hi guys. So the two activities we're doing this week are very much like what we've done in section 3.2 and 3.3. They're really just applications of exponential functions. So you're going to see these first few examples. Really, they're just extra examples. Everything in here we really know how to do already. So we're starting with an example about population growth. Currently, North Carolina has a population of 687,000. In 2008, they're talking that year. And they're saying that it's going to increase at a constant percent rate of 3. So again, the linear would be a constant amount of increase. This is a constant percent of increase. So they want us to determine the population 2009, just 1 year later. So if I'm going to take that current population, which is 687,000. And I'm going to multiply by, just like we did in the past, if it's a 3% increase, I'm going to multiply it by 1.03. The 0.03 is the increase right here. And remember, the 1 is the initial. Okay, so once I multiply this out, I end up getting 707,610. Okay, so that would be in 2009, that would be the population. So now they're having us determine the population 2010. So again, I'm going to take the last one and times it by, it's another percent, same 3% increase. And I'm going to get my new population. So in 2010, it would be 728,838. Okay, so now they're having us we already know how to do C, D, and E, really. We've done it in the past. They're having us divide the 2009 population by the 2008. And then in part D, they're having us divide the 2010 by 2009. And we did that in past activities, and we did figure out it's a common ratio. That's what it means to be exponential. That each time I multiplied by 1.03. So we didn't even really need to do that. They told us it was a 3% increase, so we knew that we would multiply by 1.03. So same thing for here. Okay, it's common ratio of 1.03. So what do you notice about those we just said? So what does it represent? This is our growth factor. Of 1.03. 3% increase. So our 3% is our growth rate. Okay, so 3%, we're going to see on the next page, they're talking about growth rate. So this is our growth rate. And then the number we actually have to multiply by to have it grow at 3%, that 1.03, would be our growth factor. Okay, so they're just talking about the difference between linear function and exponential. So linear functions would be like if it grew 2,000 every single year, a set amount. Whereas this one there is something that's common to each growing year, but it's in a percentage. Okay, so here they're going to have us fill out a table. We already did part of it, but they're actually going to have us do it in thousands. So let me fill out this table using, so t equals 0 is that first year. So they gave us that was 687,000. They're just putting it in thousands rather than the full number. And they're rounding some of these. So the next one was that we had found was 707,610. So we're going to write it as 0.6. And then the next one, if you round it to the nearest thousand, and then if we keep going, timesing by 1.03, this is what we get. Just timesing each previous one by 1.03 to show that 3% increase. Okay, so we already came up with this a few steps earlier. We knew that from previous. So write the exponential equation in that form. Okay, where A, remember, is the initial, B is our growth factor, and P is, this was going to be for population. So for this one, our population for any given year past 2008 would be our initial 687 times our growth factor is 1.03 to the t. Okay, and so this 687 was our A, was our initial, 1.03 was our growth rate, growth factor. So write the growth factor 3% as a decimal. So that would be, if I wrote it as a decimal, then we would have it as 0.03. And then they're showing add 1 to the decimal of the growth rate. So if I add 1 to that, so 1 plus that 0.03, that's what they're calling this B, our growth factor. They're just trying to distinguish between those two names. Okay. So next thing, they're just going through the difference between B and R. I mean, obviously one comes from the other. If I know R, then I just add 1 to it to figure out what I have to multiply by each time to get that growth to happen. Okay, so they're giving us a couple examples. So let me just go down here a little bit. These ones are already done for us. Okay, let me go to this one. Okay, so determine the growth factor B for a growth rate of 8%. Okay, so our growth factor would be 1.08. Solve the equation for the growth factor for this one. So up here, they gave us, B equals 1 plus R. So the next thing they're just having us do is take that equation right there and solve it so that we have one for R as well. So if we said what's the formula for R, we would say that that is B minus 1. Okay, so if I wanted the growth rate and I knew what the growth factor was, well, I would just subtract 1, just the opposite of what we just did. Okay, so let's see, example 3. Determine the growth rate for a growth factor of B equals 1.054. So I don't have to use any of these formulas. If I look at this, and if I know that every year or whatever this problem is about, if I'm multiplying by 1.054, the 1 is just keeping the initial amount going, and then the 0.054 is our rate. So this means that this would increase by 5.4% for each year or each X, whatever the problem is of. Okay, so that's my growth rate. It's just without the 1. Now when we have a decay one, that's a little bit different, but we'll get to that one when we move on a little bit. Okay, so we did the same exact thing. I'm just going to, you can stop the video for a second. I'm going to fill out this part because we've done these tables many, many times, writing it as a power. These boxes aren't big enough. Okay, and we already had these values over here from our other table. We'd already done our calculations out. Okay. Okay, so use the pattern in the table to help you write the equation for P of T, the population in Charlotte, where T equals 0 is the year 2008. Okay, so if I wrote that, you're going to find some of these activities are a little bit repetitive, but you're going to find I have the exact same thing, right? We already wrote it this way. Initial times 1.03 to the T. Okay, so here we have example 4. Determine the growth factor and the growth rate of the function if we've got that exponential function right there. Okay, so I'm just going to go and identify everything. So here's our A, that would be the initial, whatever this is, and here's our B. Okay, so we know that our growth factor, we know each time in this problem we're multiplying by, I'm just going to call this GF, growth factor is 1.7, because that's what we're multiplying by every time. Each time we plug in an X, we're raising 1.7 to that power. And so that would mean that 1 just means we're keeping that initial 250. And our growth rate, that means it's every time we move up an X, we're growing 70%. Okay, so our growth, we could write it either way. We could write it as 0.7 or 70%. Okay, so they actually had already done that one for us. Okay, so let's see. So they're giving us another example of the growth rate of a function is 5%. Determine the growth factor. I know the answers are right below, but let me just go through. If I want to grow 5%, then my factor must be 1.05. 0.05 in order to get a growth of 5%. Okay, if I only multiply by 0.05, I only get that amount that I should increase by, and I have to always keep adding back the original, but multiplying it by 1.05 does that already.